Welcome. We're now going to turn our attention to Millikan's oil drop experiment. This is the experiment that was done in 1909 by Robert Milliken and his associates to determine the electrical charge, the fundamental electrical charge on an electron. By now, I hope you have actually read about this experiment because this is just the prac that goes with it as a simulation. In a few more moments, we'll be squirting some oil into our oil chamber over here, into our charged plate chamber, which has a positive charge at the top and negative charge at the bottom, which has a separation of a certain amount of voltage. We'll be able to see the size and measure this suspended oil drop by using our telescope. So the secret of this this experiment is that this oil drop, once it becomes electrically charged, is that the upward force, or the upward electrical force given by QE, equals the downward gravity force, weight force, which is mg. The parameters that we're going to be using is that the oil that we're using has a density of 900 kilograms per meter cubed, and that's just what the simulation uses. Also, the simulation uses a distance between the upper and lower plates up here as 3 millimeters. Just for reference, here are the formulas for sphere, voltage across parallel plates, and the electrical charge. Okay, we're going to be recording our data in this table. Please note the units up here, so be very careful when we are calculating them. Okay, so let's start. I'll lead you through the first one. So what we're going to do is go to the lab and press begin. Now, to get the oil into the chamber, we press the bulb. Okay, and hopefully we get a suspended oil drop, and that suspended oil drop comes with a voltage of 13 volts. Now, the only thing that's missing in this simulation is that Milliken used an X-ray device to remove the a certain number of electrons off the oil drops. This has just been emitted here. Right, to see the oil drop, we now click on the telescope, and there is our oil drop. Okay. All the data that we need is over here, just to remind ourselves. The oil's density is there, 3 millimeters apart, and this one used 13 volts to get this oil drop to suspend. We can measure the volume of this oil drop by measuring sideways here. That's 450 nanometers. So let's record that. So we record it as 450 nanometers. And now we're going to calculate its volume, and we want the exponent by 10 to the minus 21. So let's now calculate that. So the volume of a sphere is 4/3 pi r cubed. And so it's 4/3 pi, and the radius was 450 times 10 to the minus 9, because it was nanometers cubed. Putting that into our calculator. Oops. The radius is 450 negative 9, and it's cubed. Okay. So that's that value there, but we want it to be by 10 to the minus 21 for our table. So I'm just going to press the engineering key, and that gives us 381.7 by 10 to the minus 21 meter cubes. Okay, so recording that into our table, that's 381.7. We now can work out the mass. Okay, to work out the mass, we're going to use the density. Now, the density is equal to mass over volume, so mass would equal density times volume. So the mass would be, the density is 900 kilograms per meter cubed times the volume, which is 381.7 by 10 to the minus 21 meter cubes. Okay, that per meter cube and that one will cancel, and we just simply multiply this number here by 900. And that gives us 3.43 by 10 to the minus 16. Let's see what units we need. We need this to be by 10 to the minus 18. So just setting that engineering key, and we get 343.5 by 10 to the minus 18. Okay. Right, now we know the mass of the oil drop. We can work out its weight, and that's just multiplying that number by 9.8. I won't go back to the other screen. I'll just multiply by 9.8 for you. And we want to have an exponent of 10 to the minus 15, and that gives us 3.37 down into two significant figures. Okay. We read off the voltage here. The voltage that was required is 13 volts. Okay. So we just write 13 here. Okay. And we're going to use the, we want to find the electric field strength. And the electric field strength is equal to voltage times, voltage equals ED here. So we can use that formula. So let's just work that one out. I'll go back to the, yeah. Now we know that voltage is equal to ED. We want to find E. So E is V on D. And the distance between the two plates is 0.003 meters. That's 3 millimeters. So E would equal 13 volts divided by 0.003. And so we get 13 divided by 0.003. And that gives us 433.3 newtons per coulomb, or if you want to use volts per meter. Okay, so let's record that in our table. And that becomes 4333.3. Okay. And finally, we can work out the charge on this electron, not electron, on this oil charge by using the last of our formulas, which is, let's go back to full screen, that we know that F equals EQ. Now F, this F here is the upward F must equal the downward force. So the upward F is EQ, and the downward force would be mg. So we know that mg would equal EQ, and we've just worked out the weight force here. So E would equal the weight force, which is mg on, I should put that on. Q is equal to the weight force on E. Now the weight force was, let's go back, the weight force was 3.37 by 10 to the minus 15. And the, let's put this back on. So the weight force was that there, divided by the electric field, which we just worked out as 4333.3. So doing that division, we get 3.37 by 10 to the minus 15 divided by 4333.3, and we get 7.7, we'll make a 7.8 by 10 to the minus 19. So we'll record that last one in here. Now it's already by 10 to the minus 19 up here, so I'm going to just record 7.78. Okay. Rightio. So I'm going to now complete more examples. I want you to complete this table by going at least 5 or 6 more on your own sheet. Okay, and then I'll unpause the video, and then we can continue on. Okay, now that I've completed another 6 of the performances of the Milliken oil drop experiment, I've now calculated my charge over here. Now, on your worksheet, you'll have an extra column over here, which I've now put in. And what you're going to do is take this value here, which is the Q by 10 to the minus 19, and divide it by what we now know as the fundamental charge, which is 1.602 by 10 to the minus 19. A quick way of doing this would be just simply to take this number here and divide it by 1.602. My first one that I had prepared beforehand as an example was 11.2, and that gives me 7.0 near exact. The one that I did in front of you gave me 4.9, and here are all the values. Okay. Eventually, we will get down to having, say, a 3.2 and maybe a 1.6, and you get 1. What this is saying is all of these, if you notice them, their 4.9 is approximately 5. This is 7. So this is saying that this is exactly 7. This is 7 times a fundamental charge. This is 5 times a fundamental charge. This is 3 times a fundamental charge. So Milliken realized that these all had a lowest common multiple, and the lowest common multiple was this value here, which is 1.602 by 10 to the minus 19. So your data will be slightly different, but you should work out that it will be that these are all multiples of 1.602. So the lowest common multiple will be 1.602 by 10 to the minus 19. Okay. Right. Now, your accuracy would be how, if you could work it out, what is your fundamental charge? What do you reckon is your lowest common multiple? I would say these are pretty good here. So if I divide that one there by 3, I can work out what my fundamental charge would be, and then I can use the accuracy formula to determine how accurate I was. Now, the last question here was Milliken's value that he got wasn't actually 1.602 by 10 to the minus 19. It was slightly less than that. And the reason being is, why did Milliken get a smaller value than we now accept as 1.602? I just realized that was a mistake there. He didn't take into account in his first calculations the buffeting effect of the motion of the air in the tube. That was taken into account subsequent experiments. Now, we've only done 10 here, and you might have done less than that. And he did hundreds of these experiments, and he had hundreds of numbers to determine his lowest common multiple. So when we get up a value for an electron as 1.6 by 10 to the minus 19, after only 9 or so reiterations, we've done quite well. Okay, so I hope this explains how he performed his experiment, and that you yourself have performed a simulation of this experiment. Thank you.